So we continue our series of distinguished lectures supported by the Simons Foundation. So we're very grateful and happy and thankful to be invited today by Professor Andras Szenes from Geneva, who is going to tell us about intersection cohomologies on Moduli spaces of stable bundles. And let me say that Andras is an expert on numerical geometry, and singularity theory, and many other things. So he started in mathematical physics and functional analysis, but today he is in the big community of algebraic geometers and topologists. And so he is very famous with his work on Verlinde conjecture, which he proved for the first time in the case of SO2C, sorry, SO2. And so he continues to work on the intersections theory on the Mozgovoy space of bundles. And we will hear more about this today. So let me play on you. A great scientist, humanitarian, and friend of mine for many, many years, Andras Szenes.
Oh, thank you so much, Camilla. You're very kind. And so I'm happy to talk today about some very recent work. This is just being written up, and I hopefully as we speak, even though it's rather late. And this is sort of a new development in calculating intersection cohomology of stable, actually semi-stable bundles. So actually the title has said intersect cohomology and stable bundles. So as you can see, this is joined with Camilla Felisetti and Olga Trapeznikova. So Olga is my doctoral student in Geneva, and Camilla used to be my postdoc, and now she is a position in Italy.
I like the family name of the Russian lady.
Pardon?
I like the family name of the Russian lady.
That's right. Yeah. I wonder if you know what that means.
I do.
So tell us. No, but we'll do this afterwards, okay? Let me first tell her what she's done. Then we can appreciate it more. Okay, so Ludmil, I was a little, because it's a lecture, it's a two-lecture series, and Ludmil told me the first one should be really colloquium, so of course I don't know what that means precisely, so it will be very basic. So if you know what, if you know about homology of algebraic varieties, then you will not learn very much today. So first, for those who don't work at all in enumerative geometry, I wanted to explain a little bit what this is. So just give you a minuscule introduction to enumerative geometry. So enumerative geometry is basically the arithmetic of geometry, countings. And so the first basic enumerative problem is, the first non-trivial enumerative problem, rather, is counting the number of lines in free space which intersect four given generic lines. So that's the first non-trivial enumerative geometry problem. So how many lines are there generically? So the correct answer, in fact, is well over the complex numbers, but it's 2. So the number we're looking for is actually 2 for a generic situation. Okay, so and I'd like to a little bit explain how this 2 will come up. So we need to do a little manipulation instead of the language, and so that's what I'll do now. So how does this 2 come about? So first of all, we'll instead of first of all we pass to complex numbers, of course. So we look at complex free space and complex lines. And then we sort of compactify the situation. So this is what I trying to show you. So this parallelogram is actually the 3-dimensional space, and all these pictures in 4 dimensions. And then we put it in this kind of at height 1 from the origin. And so then you can see that the lines in these 4 lines in C3 that are drawn on the left are actually inside this parallelogram. And each line then gives rise to a 2-plane in C4 but this 2-plane is linear, so that goes to 0. So of course, if you have a 2-plane in C4, then it will intersect this 3-dimensional plane in a line, and that gives you a line. So there's a correspondence of lines in C3 with 2 planes in C4, and the set of 2 planes in C4 is denoted by GR24 for Grassmann. Okay, so that's the first thing we do. Of course, the point why we're doing this is because, of course, this space is better, it's compact. Of course, this has a little more lines than this because there are some lines that are parallel to this plane, and then they will not have a trace like that. Okay, so we place this in this compact situation. And then we do the following. So then we try to set up intersection theory. So we do the following way. For each of the 4 lines, so a CI will go from 1 to 4. For each of the 4 lines, so these are, let's just say L1, L2, L4. We set up a CI, a subspace in this space, the Grassmannian, so 2 planes in 4 space, with the following properties that will look at we look at this line Li, and then we look at all those lines in the Grassmannian which intersect the line. Okay. And so then it's pretty obvious, and what we're looking for is that the intersection of these four sets, C1, C2, C3, C4, this will be a finite set of points, and the intersections actually is going to be these 2 red lines. So, so just for the dimensions, I mean, I didn't write them, but so this is a 4-dimensional space, this Grassmannian, and these are codimension 1 spaces. It's a codimension 1 condition to say that you intersect the line. And so, so codimension 1, codimension 2, 3, 4, so this will be codimension 4 in 4 dimensions, so it will be 0-dimensional, this intersection, and you just want to know the number. So that's the idea, and so of course you still need to calculate it, but we have now a setup for it. So I introduce one more thing, one more type of thing. We can also just fix a point, so this point is in 3-dimensional space, and we fix a point and we can look at all the lines that go through that point. That gives you a different type of subset. I'll denote that by QP. So, so then we organize this thing in something that's called the cohomology, and so I just want to introduce cohomology. Using this setup, and it goes the following way. So you grade things by this codimension, and now the reason you have these numbers here is because you look at real codimensions, so that's why everything doubles. So I said it's C1, C is codimension 1, but the real codimension is 2. So each of these C is represented by the same symbol here, and you just say you write so in degree 2 you just have this C. Then when I intersect 2 things, I represent here as a product, so I'll call this C squared, C cubed, C to the 4th. C to the 4th actually represents this intersection. And then in addition, you have this cube here, which is the set that I described. So these sets actually now the idea, the logic is that the intersection of these sets is represented by product, and so intersection is associative. The product is also associative and commutative. And so you write down all the questions, all the relevant sets. And so it turns out that I already listed here all the relevant sets. So that actually is the full what's called cohomology. So cohomology is all the relevant questions you can ask. So all the relevant sets of lines that you can describe in the Grassmannian of 2 planes in 4 is this 1, 2, 3, 4, 5, 6. Okay, so once again, so this is sort of the whole space. This is the space of lines intersecting. One line, C squared, the space of line intersecting two lines. Q is the space of lines going to a point, etc., etc. And this is what we want to understand. So now what is happening is the following: is actually the eighth cohomology. So this piece here is canonically isomorphic to Z, it turns out, and so then actually we just evaluate in order to describe and answer all the questions we can ask about lines. In three spaces, we do the following: we evaluate any of the possible monomials that end up in this top degree. Okay. So actually, let's stop right maybe I want a C basis. Okay. All right. And so the answers are here. If we want to, for example, find the number of lines that go through two given points, P1, P2, then the answer to that will be what I call the integral, so this isomorphs here of Q squared, and that is equal to 1. If I want to know how many lines go through a given point and intersect two lines, I get this one. And the answer, the original question that I asked, here this is the integral of C to the fourth, and that is equal to 2. So that's the sort of in this setup, that's how we get the answers, the organized answers to enumerative geometric questions. Okay. So now I just want to now formalize what this object here is. That's called the cohomology package. So let's M be a smooth-oriented manifold. Then, like the Grassmann is one of the examples, then you can associate to it the cohomology ring. So that's an graded ring, which goes from 0 to the dimension of M. But dimension now I will mean by dimension the real dimensions. So for the Grassmann, that was 8. So it's a graded commutative ring for the reason I explained. And then, so the package, I mean, what we know about is the following. So there is, first of all, so when I go to dim is the top dimension. So the dimension that I pass to just rational coefficients for simplicity, so everything is over Q now. So then this ring, which I can associate to this to any manifold again, the top cohomology is canonically isomorphic to the Q. So there is this integral map, if you like. And then the following things are true. So this is again a commutative ring, but it has a pairing on it. So which goes the following way: if you take the L cohomology and then dim minus L cohomology, then because it's graded, you end up in dim M. So in this piece, in this part, and we say that this is a non-degenerate pairing for any L. Okay? So this is true for any L. That's called Poincare duality. And we also introduced what the Poincare polynomial is, which is the generating functions of the dimensions of the pieces of the cohomology. So I'll stop here for 1 second. So basically, the general philosophy in enumerative geometry, there's kind of two schools. So some people calculate, in fact, these integrals. This is called intersection numbers. So you answer questions answer enumerative questions, and this is what I like to do normally. And then there are other people who are a little more lazy. They actually calculate just this Poincare polynomial that I wrote down here, which is just essentially is a description of the complexity, sort of topological complexity of the manifold, of how complicated it is, but it doesn't really tell you anything about, answer any real enumerative questions. Okay. So, but actually, it's today in this work we actually deal with this kind of numbers, nevertheless. But this is a much easier problem. So our goal will be to calculate these Poincare polynomials for certain spaces. Okay. But so there's this deviation. I just want to emphasize that the more interesting question is actually the numbers. Okay. So now yeah, just for the package, we have one more thing. Well, there's the famous Kenneth formula, which just says that if you take this product of two manifolds, then it's the tensor product of the two rings, and that implies, of course, that the Poincare polynomials are multiplicative. And also sort of the Lefschetz statement. So for this, I will assume that it's some kind of complex algebraic variety. So the smooth-oriented manifold is given by complex algebraic equations in projective space, homogeneous ones. So then the claim is that there is a special class in the two-dimensional homology such that it multiplying by this class with the correct power will take you to from L to D minus L. That of course is not a statement, but the statement is that this is isomorphism. And finally, so just going back to where we were in the Grassmannian, what we're doing is so this is, for example, an example of Poincare polynomial. As you remember, there were this double two classes here, C squared and Q, and then the other ones. So this is an example of Poincare polynomial. The purpose of this work is to calculate a much more complicated one, but we want to get some formula like this. You'll see at the end. Okay. So, but that's what I call the cohomology package, the basic one. Okay, so let's discuss now the spaces that we will study. Okay, so there are called moduli spaces, and normally in the numerical term, that's what you're interested in, intersection theory on spaces which classify things. So moduli spaces just roughly means it's quotient spaces. I mean spaces that were of objects up to isomorphisms. Like for example, I look at the moduli spaces of triangles, say in the plane. So modulo the isomorphism, metric isomorphism, they're identical. So now this is a more complicated thing, and actually there are more natural ways to define it, but they take longer. So now I will just, this is a slightly less natural setup, but it's quicker to do, so that's why I opted for this. So our protagonists are actually two spaces, M0R and M1R. R is just an integer, right? It's going to be the rank. It's the dimension of a vector space. So what we do is, so UR is the rank R unitary group. So it's R by R matrices, a group of R by R matrices, a unitary. And the setup is that we will fix a Riemann surface sigma g, and really what we are looking at is what's called the moduli space of flat connections on this surface sigma g. But for simplicity now, I'll just define what it is in a direct, straightforward manner as a set. And it goes the following way. So M0R is a bit easier. So what we do is we look at G matrices AI and G matrices BI. Again, G is the genus of the surface, number of holes. And then we do the following. This A1, B1 is a commutator of this group commutator. So it means A1, B1, A inverse, B inverse, right? That's what this simple means. And I multiply the commutators like this. This is actually just means you represent the fundamental group of the surface. And then you solve the equation that this product commutator equals to the identity. So this is an algebraic, actually a real algebraic equation, right? So it's a bunch of matrices. So you take the product of 2G copies of UR, and in that product you solve a single matrix equation. So that's pretty complicated algebra. If you look at it, as I said, it has a more natural geometric description, but so let's skip that for now. We'll come back to it. So you do that, but then, so because that's why it's called the moduli space, each of these gives rise to sort of flat connection, but there's an identification, because you have sort of made a choice of basis of the fiber, and so actually this symbol means that you divide by an action of a group, in fact, and it's the action of the group UR for each element. You just do the diagonal sort of conjugation by the element C of each of the elements. It's quite obvious that this preserves this if you conjugate each matrix by the same C, then this equation will be preserved. So this action acts on this set, and what we're interested in is the quotient set. Now, this has a very clear topology, right? Because this is just the product of 2G copies of UR, which is a perfectly good, smooth thing. Then you solve your equation. Well, that might not necessarily be smooth, and then you divide it by a compact group action. It will still be a nice compact manifold or a nice compact space. Okay, so that's always okay. Okay, so then now the second one is this M1. So M1 is the same story. The only thing is that now I will instead of the identity, I require that this is so epsilon r. Epsilon r is so this is just a primitive r root of unity. Okay. And so you multiply that the identity image. So that's this M1R. So these are two protagonists. These are two spaces. We'll try to understand the cohomology of these spaces. So invariant that I just introduced. Okay. Maybe one little remark here I put in on the side here. There, if I look at M01, then that's a very simple story. So if I take 1, the rank is 1, then U1 is just the commutative group of unit complex numbers, right? And then this, of course, that's a commutative group, so these commutators, A1, B1, A inverse, B inverse, so then they're equal to 1, each of them equal to 1. So this equation turns out to be vacuums. So then you don't need to do anything with that, and the conjugation also acts trivially, so then it's just 2G copies of U1, as I said before. So that's what you get. Okay. So these are our two spaces. The goal of these lectures is to study the cohomology of these spaces.
But don't you can think
Is
this ER to be K?
Epsilon R. Pardon?
Yeah, but I mean, you can also consider other.
Yes.
So,
I'm trying to do a minimalistic thing. Obviously, for any power of epsilon, you'll get, and in fact, you get some things that are non-equivalent to these, so you get some other spaces. I'm giving the absolute minimum. For us, actually, it's a bit surprising, but in fact, surprisingly, this is going to talk about only about these two spaces. So now let me go to try to explain some really one of the most fundamental notions in geometry, a very deep statement. So for that, I'll talk a little bit about complex quotients. Okay, so complex quotients, what I mean is the following. So let's look at this story with the Grassmannian once again. So Grassmannian have two planes in 4 dimensions. There's an obvious way to calculate also as a moduli space, as a quotient. So how do we do that? So what we say is that we can look at, well, I'll call it R24. What I mean by this is that I just look at a 2x4 matrices, but such that these two are as an orthonormal basis of the 2-dimensional space. So they are, in other words, these are two vectors which are orthonormal. So that means in 4 space. So that means, they have norm 1 and they are orthogonal, right? That's what I call orth24. And then here I can multiply any such matrix on the right by a 2-dimensional usual orthogonal matrix. Yeah, sorry. Yeah, I did something stupid here. It's enough by correct. So I mean they're unitary, of course. Everything is over complex numbers. So I meant orthonormal in the sense of it's a complex basis. So then I apply by unitary action on the right. Then of course this two orthogonal, we just changed another orthogonal matrix basis, but of the same 2-dimensional vector space. So I did look at the span. What I mean is I look at the span of the two vectors. That gives you a 2-plane. And by multiplying on the right, this 2-plane will not change, so just the basis will change. So yeah, and in fact, clearly this unitary action will just permute the different two-dimensional bases. So actually, if I take the quotient of this set, this is a set now, by this group, then in fact, I exactly recover this. That's a very important thing. The only little bit annoying thing is that that's wonderful, but what is this set is not so clear actually. So then it's not, you don't get so much. So there's another way where you win some, lose some, and the other way is the following. I can also just look at all matrices, so I look at all 2x4 matrices, and I can try to divide them by the actual GL2. So now if I take a matrix whose rank is 2, then this idea, what I would change, works as well. I mean, the GL2 permutes all the bases of that two-dimensional vector space. Of course, the point is that this isn't true here, what I wrote, because you need to, well, denoted by a little circle here, you need to have, well, whatever, non-degenerate or full rank, so that will just mean non-degenerate, or the same thing in this case of rank equals 2 matrices, only those. Of course, if you take the 0 matrix, that will not give rise to a 2-plane. So here you win a little bit because this matrix space, on the other hand, is linear. It's a linear space. Topologically, it's trivial. On the other hand, you need to get rid of something in order to get a quotient. Okay, so this will be our basic. The fundamental deep fact is that this is true in a very general setup. So either you this is what's called, you use geometric invariant theory, or you use some norm. And so there's this duality of these 2 points of view is very general, and it's also true for our spaces. So in particular, so the idea is that these 2 spaces, what you see here is kind of this first version. I showed you, like, there's unitary matrices, if you remember, right, that I had here, it's UR, but there's another way of looking at them when, which just looks like this. So I'll explain this now. Okay, so this is already not so simple. So the idea is that this sets now this kind of a totally different way. Okay, and in fact, to prove that they are the same is going to be not at all easy. Okay, so let's do this. So this I just copied here. There's nothing changed here. But now I will introduce the notion that you need in order to find this isomorphism. So it's the following thing. So I still take this sigma, but now before it was really just this is really just a representation of the fundamental group of sigma g of the Riemann surface of genus G. Now I will assume that sigma g has a complex or holomorphic structure, and I'll look at holomorphic bundles over this complex one-dimensional manifold. So this bundle is now a holomorphic bundle. So the way to imagine that is that for every point of the surface, you associate a vector space, so it parameterizes a family of vector spaces, but all together they form a complex manifold. So this V, the total space of V, is still a complex manifold. It's a holomorphic structure which is compatible such that when you do this map, it's a map of complex manifolds from V to sigma. But over each point of sigma, you just have a vector space, a complex vector space over rank R, right? So that's the R. Now I define a rather exotic looking notion which is called stable. This bundle is called, the V is called a bundle, a holomorphic bundle is stable if the following thing is true, that if you take any proper subbundle, so subbundle, this red thing is subbundle, over each point you take a subset, a linear subspace of a certain rank, that rank is F. So the rank of V is, say, R, and the rank of F is smaller, strictly smaller. So here we assume that it's a non-trivial subbundle. So by subbundle, again, we mean that for each point of sigma, we associate in a holomorphic way a subspace of a certain rank F. Now there's a topological invariant of bundles, which is called the degree. The degree is just the degree is just an integer, and this quotient between the degree and the rank is called the slope, and basically the bundle is called stable if this slope is if there are no subbundles which have equal or larger slopes than the ambient bundle V. So this is not so easy to understand if you've never seen this. So for now we can put in parentheses. It's a certain rather exotic condition. Okay? The point is that this condition is in fact is equivalent, is the version for bundles. Just a second. Doesn't want to show anymore. Okay. But so this is a version of what I wanted to show here of this little thing that we had to throw away from all matrices. So normally, instead of taking all bundles, we'll now only take stable bundles. Okay, so for example, this M1R, so that's actually turns out that's a bit simpler. So this M1R has a different sort of appearance, and it's the set of rank R, degree 1, so this degree is this invariant of bundles, where V is stable. So if you take the stable bundles up to obviously up to isomorphism, then they actually are in one-to-one correspondence with this set. I mean, this is a completely insane statement. It's really, as I said, it's one of the sort of deepest statements in modern geometry between stability and sort of some metric existence of metrics. When you go, but we just accept this. So now for M0, it's a little more complicated because it's clear why. So let's just look at why that is the case. So let's just assume, say, R is 2 for simplicity. If R is 2, then this number, the degree of V is 1. It's always 1. And the rank of V is 2, so this is equal to then 1/2. Okay, so in this case, so here if R is 2, then this this degree divided by rank is equal to 1/2. Okay. All right, so the slope of V is 1/2. Well, if I take a subbundle, that can only be if the rank was 2, a non-trivial subbundle has to have rank 1. And a rank 1 bundle always has integer slope. And so that means that this degree F can never be equal to this. It can be bigger or smaller, but never be equal. So that's very good. This is not true if the degree is 0. If the degree of V is 0, obviously this subbundle can also have degree 0, and then their slopes are equal. And that causes some problems. So in fact, the correct equality, if you want to find what corresponds to M0, is the following. It's a rank R bundle again with a degree 0, but now what you require is that V is a direct sum of stable degree 0 bundles. So this is actually a true statement. It's also not very trivial. Okay, but this is so anyway. This is a new incarnation which corresponds to that complex quotient world. All right. So, and for our calculations, this other thing, even though it looks more complicated, it turned out to be much better. Right? That's a complicated fact. Okay, so now we have two descriptions, just to recap. One of the same space, one which says that it's, for example, this M0, which says that it's just a quotient by a compact group by some equation, and the other is a classification of the certain types of holomorphic bundles on the Riemann surface. Now, of course, why this looks more complicated, because this space is actually smooth, the space M1R, and this is going to be singular, and of course this will play a role why this is more complicated. Okay, so let's then try to discuss a little bit as I announced, what we're going to work on is just understand the Poincare polynomials of these spaces. So the goal of these lectures is to actually calculate the Poincare polynomial of M0 and M1. So I don't know why it sometimes starts off. So now I will tell you this is the first thing that our main focus will be understanding the topology of M0, but I'll start with M1. And M1 is a classical case, and I tried to give a hint of what happens there. But actually, I will, since that's not our goal, it will be a bit sketchy. I explain. But so I'll introduce a notion which really doesn't work. And if you start learning elementary algebra topology, you know it doesn't work. And this is this cut and pasting. Of course, well, what you want is that suppose you have some space X, and let's try. And then it comes back somehow. Now it doesn't work. Okay, so I'll try it one more time. Eventually will come back. But anyway, so as you see here, you have a space X, and suppose you cut it into disjoint pieces. And what you really want is that what would be really easy, that if these disjoint pieces are relatively simple, then what you can hope for is that the cohomology ring of X, in some sense, is going to be some sort of, at least as a vector space, is a direct sum of the cohomologies of these pieces. Okay? And so when you it's like, don't try this at home, it's that sort of thing. So when you start doing topology, the first thing they tell you that this is not true, so don't even try it. Okay. So the point is that actually it is true in these cases that I described, and this is rather surprising. So why do the people say it's not true? Well, the reason that they say it is because these are very complicated spaces. It's just, even the smooth one is very, very difficult, very complicated. And so if you take this M1R, for example, this is a million, it's R squared times G minus one dimensional space, huge space, very complicated topology. I mean, the only way normally we know how to calculate topology is to cut it into these, cover it with these kind of trivial patches, and glue it together, and then understand the combinatorics of that. And that's just, nobody ever managed to do that. So that's just an infinitely complicated thing. So it's really remarkable that something this simple is actually true for these spaces, but it is true, and this was a discovery of Atiya and Bott. So let me explain I'll do a little bit of an introduction, just the flavor of this. It's not, I will not actually explain it completely. So the idea is the following. So I'll explain it first in this Grassmannian example. I look at this Grassmannian 2-4, and as you remember, I had to cut some pieces out, the non-rank 2 matrices, and then it was okay, a quotient. In fact, what the point is, what you can do is that you can, we can look at the stuff that you threw out. So look at the matrices which do not have rank 2. So all matrices, you subtract the matrices of maximal rank. So what's left is matrices of non-maximal rank. So you have two kinds, rank 1 and rank 0. Because rank 0 is just a 0 matrix. Rank 1 is, rank 1, 2 parallel. That means you have 2 parallel lines. Two parallel columns. One is a multiple of the other one. And so the idea is that you look in this set, we'll look for points with non-trivial stabilizers. So of course, so if something is, for example, rank 0, so you have the 0 matrix, then it is stabilized by the entire group. GL2 stabilized 0. If they're parallel, then there's a smaller toric, a C star group that preserves that matrix. So you see, the point is that of course, the action of this group on these sets can have stabilized, and we want to classify that. And it's basically what you're going to do is here X will correspond to all matrices, so it will be something trivial, and these pieces will be sort of the Grassmannian or this matrix 0 thing, and then matrix circle thing. And then these other pieces will be the other kind of matrix. So here, if you like, you have 3 kind of pieces. You have X0, which is roughly the Grassmannian. X1 is the rank 1 matrices, and it will be an X2, which will be the rank 0 matrices. I'm just giving you a very sketchy understanding of this. And then finally, this way you'll get an equality. The cohomology of the X, the whole space, will be trivial, and it will actually be the sum of the cohomologies of these 3 pieces. And by subtraction, you can subtract from the cohomology of all matrices, you can subtract these 2 pieces, and this way you will recover this. So that's the general idea. It's a subtraction argument of sort. Okay. So I will not explain this strategy. You can do this exercise at home, but I will explain the Atiyah-Bott formula, which works for our moduli spaces, and it looks as follows. So so this was the idea of a seminal paper of Atiyah-Bott, the Young-Mills paper from 1982. Which roughly, I can only give you, as I said, a flavor. I won't go to M0 after, so I'll just give you an idea of what it looks like. So it works as follows. So the equation is that I was talking about, this x, x0, x1, etc., looks as follows. So this, first I'll just write down the formula that you get out of it, okay? And then I'll explain a little bit the geometry. So the formula is as follows. So this P2 now corresponds to this, is the cohomology of this x. And then this P2, PTM12, of course, is the space, the Poincare polynomial M12 that we're looking for. That's the quotient. And then there's a bunch of pieces, those rank 1 pieces that you have to add. So this is this, and so this, if you like, is this additivity, this equation is the Poincare polynomial version of this equality here. Right? So you take this equality, additivity of cohomology, you pass the Poincare polynomials, which just calculates the dimensions of the cohomologies on both sides, and get an equality, and that's this equality. And so this is, again, this is the piece we are interested in, and this is an infinite number of pieces that appear. So for the bundle case, as opposed to the cross one, you have an infinite set of pieces. And then the result is something trivial. Okay, so that's sort of the vector space. That's its matrices, if you like. So to be a little bit more precise, as I said, I'm not going to be completely precise. Something like this. So if you want the geometry that's behind this, then you have here M12 is to its correct. So this partition I explained. So M12 is the partition, and then here you have some trivial space, sort of, and then here you have an infinite set of types of bundles, which are basically sums of two line bundles in a certain sense, which are now, so one of them is degree n plus 1, the other is minus n, and you can easily verify that these are exactly bundles. These bundles are not going to be stable because they have a sub bundle whose degree is bigger than the slope than 0, or than 1/2. The slope will be bigger than 1/2 for this line bundle. So anyway, this is here you see a list of bundles that are not stable, and actually there each of them will give you a contribution, and for each n, here you see the infinite set of contributions corresponding to this infinite set of bundles. And it turns out that this space A is a certain set trivial. It's a little more complicated than that because you have to pass to equivariant cohomology, which I didn't explain. But anyway, the final answer is the following. So I'm going to explain it right now, what is what. So again, of course, so this is just PTM12, the thing we wanted to calculate. And then here, this is why I wanted to show you this. You have this P1T squared, and this P1T squared, as you remember, is exactly the sort of the two rank 1 cases. You remember, for the rank 1 case, the formula for the cohomology was 1 plus t to the power 2g. Or that was the corresponds to the Jacobian, right? So the complex sense. So you take two of these bundles, and so that's why you have a square, and you have to divide it by 1 minus t squared because actually it's stabilized by the corresponding action. So in any case. And so then this A, this is a little mysterious that I will not explain, but in a certain sense it's a trivial factor that corresponds to this A. In any case, so this requires, of course, it's a long paper, I'm going to say, tell you all about it, but the point is that this can be easily calculated. This is fully factored. This is this A, and once you subtract this infinite sum from it, which you can write it here. I use geometric series to now write it in a rational function. Once you subtract these, take the difference of these two things, you get the formula that you're looking for. That's the idea.
Let me just mention that actually for this case, this was done by Kado and Riemann before.
So actually, okay. So once we're here, so let me just mention that actually it's not exactly true. So that
I mean,
let me tell you the story. Since I was a student of Bot, so I can qualify. It is mostly true, but just not 100%. So the story was as follows. It's really incredible, actually. Yeah. So it's certainly the formula. Actually, they didn't quite have this formula. Actually, was Dessalines and Ramanan who rewrote it then in this form. But they were definitely their work. Actually, they were motivated the work of I.T. Bot. But the amusing, so it is true actually. But the amusing fact is the following: is that in fact what they were doing, there was Delim, there was the wave conjectures, and so in fact nobody was hoping as usual to prove the wave conjectures. Instead, what happened was that Harder and Arsiman, they decided to check the wave conjectures, and so to check, so there was not no. And assuming the wave conjectures, they calculated these Betti numbers. And so, in fact, they were not proving it, they were checking it for assuming the wave conjectures. And while they were doing it, they improved the wave conjectures. And so the theorem, they calculation became a theorem. So in that sense, right? But actually, they purposed originally when they were doing it, actually it wasn't, it was using something much more complicated. But of course, that is true. I should have mentioned that they worked as well. But now, this way of thinking about the geometric field, etc., the way I describe it is the idea of I.T. Bot. It's true that the formula itself, they were motivated actually by this formula. That's how they found it. So, all right, so that I'm done with this. So I gave you a sketch of how I.T. Bot did do the calculus for the smooth case. And now we pass to this more complicated world. The problem is that M0 is not smooth. And the general idea is if something is not smooth, then cohomology turns out is not a very good invariant. In particular, out of the package that you have, I described for you, you still have cohomology, but like most of those things are not true. Okay, so the Poincare duality is not true. I mean, most things are not true. And so Goretzky McPherson invented in the late 70s, 80s, and what's called intersection cohomology, which is a perfect replacement for usual cohomology. The only problem is that it's really complicated to calculate. And so I'm very proud that we actually did this, basically by hand. We calculated the intersection cohomology M0, and that's what these lectures are about. So let me just quickly tell you the package, go back to that package that we had. So this is now the intersection cohomology package. So now we don't assume anymore that M is smooth, so M can be singular, and then it looks very similar. So there's this thing that it has to be stressed, so not absolutely any singular. That works, but any algebraic variety will work, so you can assume. And mostly we will be interested in this setup when M is a complex projective algebraic variety. Okay, so is stratified, it's true, is there defined for any stratified topological space, but we are only interested in this example, so we'll assume this, okay, and then this is automatic. So the point is the following: is still a graded space. It still goes from 0 to M. Of course, the main point is the only thing you lose, the big thing to lose, is not a ring, no multiplication. So no multiplication. So that's a big loss, I have to say. But you get a lot in return. So in particular, of course, so first of all, it's a generalization of usual cohomology. So when it's smooth, it's just the same thing. Poincare duality is still true. You can define, and it's just a definition, you define the intersection Poincare polynomial. The Kuhn formula is true in this case, the complex projective variety case. That's not always true, but here it is going to be true. And the Lefschetz principle is also true. So there is still an element in cohomology intersection volumes, doesn't matter, and which gives you here this and so on. Okay. So I want to emphasize that you still get, and this is important, but I'm not going to talk about it this time, but our construction actually allows you to have access to, you still have intersection numbers of sorts. So you can intersect an element with a complementary dimensional element. That still makes sense because of Poincare duality. But you cannot take like triple intersections, don't make any more sense. So unless you're lucky. And actually, we are usually lucky. So maybe any questions about this? So this is just, I'm not going to define what it is, so I just give the axioms that we still have, which are much better than actually in cohomology. I mean, one example why it's better. So the toric varieties, cohomology of smooth toric varieties is sort of a combinatorial invariant of the data. And if this toric variety is not smooth, then this is not true anymore. So it's not just a combinatorial invariant, but intersectionally is a multi-combinatorial invariant. So there's millions of reasons which you will, I hope, partly convince you why this is a better invariant than cohomology. This is the right invariant. I didn't believe it for whatever 30 years, but now I am converted. Try to convert that. Okay. So this is our setup. So this is it. With this loss of the ring structure, otherwise we basically preserve everything. And so then I get to our main theorem. So let me try it down. So this is now a main theorem which links the intersection cohomology ring here, the intersection cohomology Poincare polynomial of M0 to the usual cohomology of M1. So there was a space M0, remember, and there was a space M1. So let's just focus on those. So let's just look on the right-hand side. Forget the left-hand side. Let's just look at this. So this is just a generating function for all ranks of the thing that ATM bought, or higher than our Riemann formula. Okay, so what is happening here? We just take M1R, and the only thing we do is just we multiply. So this is just the kind of a cross. What I mean by this is you just multiply them. Right? So you take the product space. So by the Kunin formula, you just calculate the Poincare polynomial of M1, multiplied by the Poincare polynomial, the projective space of rank R minus 1. You take, and now you take the, so here I actually don't even need this thing, because it's a smooth round. This is just an ordinary Poincare polynomial. And the only thing, there's a thing that's necessary in this is to multiply it by, to replace t by minus t. So that means the odd cohomology classes will have negative sign, in the Poincare polynomial. Right? So like for the circle, it will be 1 minus t, not 1 plus t. That's this minus t here, that's what that means. So it's just a substitution. It should be pt, it's p minus t. Okay. So you take this, it's basically just take the Poincare polynomial M1R and as I said, multiply p, the Poincare polynomial PR minus 1, take the corresponding Poincare polynomial, and then replace t by minus t. You introduce a shift here before, this is minus t1 minus. Try to revive it once again. And so. It works. Okay. So so this is basically what partners want calculated. You introduce a little shift with this minus t to 1 minus g r squared, and then you just take a generating function with a generating function parameter qr, e to the r. So that r encodes the rank. You take this infinite. This is not a very meaningful thing a priori. So let's not just go to the left-hand side. So that's a little more complicated. So actually, it's not, in a sense, it's not. I mean, you look at this intersection cohomology Poincare polynomial, and amazingly, it's just identical. These forms are identical, as you can see. This and this is the same thing, except you replace 1 by 0. That's really a kind of a stunning fact. And then, well, then you have to put this Felisetti exponential, which that's the last thing I explained today. But before that, I just said that this problem of calculating the intersection cohomology of P0 of M0 goes back to works of Kirwan at the end of the 80s. So this is again, it's like the Deline's, the wave conjectures. It's Goreste McPherson found this immediately. Frances Kirwan, let's check it, let's try it, and it turned out to be a very, very difficult thing. So she didn't quite get these Betti numbers. She got very far, but the usual technology at the time didn't allow her to calculate the Betti numbers. And then later,
She's doing France.
Pardon?
She is
Dame Frances now, yes, but I think I'm allowed to call her. And in fact, later the work. So it's now the story I'll tell you next time. So now let me just for the record. So the actual formula that we learned from is from a work by Mozgovoy and Reineke, who are motivated by work of maybe Meinhardt, Reineke, Conselli, Soibel. So there's a long story that I'll tell you tomorrow. But so this formula is not exactly completely original to us, but in this form, certainly this was found by Olga, and I think it looks absolutely fantastic. I mean, it's really there's two identical things there, which are related by the platistic exponential. Okay. And so the platistic exponential is well, I'll write. I don't have much time, but I will. Explain just very briefly what it means topologically. It's basically, the idea is that you roughly replace products by symmetric products. So platistic exponential is an operation on just polynomials in one variable. So it looks very simple in a sense, but then it's not so easy to describe. So the best way to describe it is what's called Macdonald's formula, and that's what there's several ways of doing it, but this formula, let me explain it here. So what's happening here, so we take an arbitrary space X, and let's look at its Poincare polynomial. Again, we'll replace t by minus t. Okay. And now this q is just q. So of course, when I take an infinite sum here, then it will satisfy the usual exponential property. So that just means that, you know, the exponential of a sum is a product of exponentials. So I can take each piece of the sum and apply this formula to it separately. So I'm just taking one term of this thing and I write it. You know, I explain what the platistic exponential of that is. Then I still need to take this infinite term. And it's the following. So roughly it's like an exponential, but you instead of like usual powers, you take symmetric powers of the manifold X. So what that means is that, right, so symmetric power means that I take, you remember Kunev formula, so we know that by the Kunev formula, if you take the cohomology of x to the n, then it's just going to be just the tensor product of n copies of x, of the cohomology of x. And the Poincare polynomial is just going to be the power of the Poincare polynomial of x to the n is going to be equal to the Poincare polynomial of x to the power n. It's multiplicative. So that's okay. But now what you do is you look at this x to the n as the action of the symmetric group, right? And so the cohomology also will have this action of the symmetric group, and you take the invariance of those actions roughly, and that's the symmetric power of x is the quotient of x to the n by the symmetric group, and you take the cohomology of that. Okay, you can easily, but this essentially actually is just, and I'll explain tomorrow in more detail. It's just an action is an operation on polynomials. You have a polynomial p minus tx, and this is what you get. So another way of writing it, and here is an explicit formula, is the following: is that you roughly for each for each k cohomology class, what you do is you write on a factor 1 minus t to the k q, and then this shows that you put it in the numerator if k is odd, and in the denominator if k is even. That's what you have here. And for each of them, you have a factor like this. Then you take they take the general function. That's the same thing as this actually. It's a different way of saying it. So it's just, so as you can see, this only depends, this formula, this thing here, only depends on the coefficients of this. But and it is multiplicative in that sense. So you do that, and this is actually answers the question. I mean, it's easy. See that if you know the right hand side, it's an easy. It's an inductive way you can calculate than the cohomology of M0. The intersection cohomology Poincare polynomial M0R. So this gives you a fine answer. This is a very not very similar, but a similar formula was also was found by Mozgovoy and Reineke, which motivated us. So actually, there is a formula which is quite similar, but ours has a very clear geometric flavor, which is a much more direct. So I'll explain the geometry of this formula.